My talk today is going to talk about how to do learning for the class of models that I discussed yesterday, how to do unsupervised compositional learning. And in short, if we, yesterday I wrote up models like this for horses, but how did I get it? You could hand design it, but that takes time. You don't want to do it. Also, if you have many objects like these, you would like to learn models for them which are sharing parts, and again, that's not easy to do. Things at the bottom here we'd like to learn, these automatically. I have to admit, in that paper we actually did design it by hand because I have some very energetic students who are willing to do it. But so I guess the short answer, the idea here is that I want to manage to do unsupervised learning on many classes of objects. In some cases we can, in some cases we cannot at present, and so it's an ongoing project. This, I think, is in certain areas, this is called structure induction, because we do not assume that we know the graph structure of the model. So there are several different forms of learning. One form of learning is that you have a probability model for generating the data, and you have some unspecified parameters for it. So certain of the classic deep leaf networks would be of that form. You have an input layer, you have a middle, you have a next layer, you have connections between them, you have weights, you train them by, restricted Boltzmann, things like that, etc. Here, I don't want to assume that I know the geometry. I don't want to assume I know the graph structure. I want to induce it. And at the same time, I also want to learn the parameters. The graph structure also should allow for several possibilities. So, there's a model for a single object which might correspond to a car from one viewpoint, but then I'd like to have a model that can also correspond to a car from a second viewpoint. This could be considered, I could do this by mixtures of distributions. I could have one model for here, one model for there. That would be one way of doing it. For some of the hierarchical models, they should maybe thought of more as sort of mixtures of mixtures of mixtures. So you're sharing components every way down. If I have a mixture model which has one component for this, one component for that, I'm not doing any sharing between them. So it's okay if I only need to have 4 models for cars, and I don't gain an enormous amount by doing mixtures. But if I have a large number of objects, I would. So also in these cases, we would not want to assume that we know how many mixture components there are. There are 4 here, but we don't know that when we start out. And the ways I make this easier for myself, or my group makes it easier for ourselves, and then there are ways we make it harder. So to start with, we're not actually making generative models of the image intensities, as you would if you were doing a hierarchical, classic deep leaf network. We're not necessarily trying to generate the direct image appearance. We are concentrating particularly on the spatial relations between things. And so with the appearance, we're making certain simplifications. Okay, why are we doing this? Well, partially because I think modeling the appearance of things is incredibly difficult, having worked in computer vision for a long time, and it's easier to model partial appearance. If you want to model an image, an object like a car, you could try and model the intensity appearance of the, of different parts of the car, of the tires, of the body of the car, of the windows, and it's possible you could do that. However, there's an enormous amount of variability in the appearance of a car, particularly, say, of the appearance of the windows. It's going to depend what's behind the windows, what's lighting on it. So the issue is, do you really want to model those first? And so it may be better to try and model certain features of the image which are in some sense insensitive to the variations of the object. And the variations would come from, say, different lighting conditions. If I move around here, you're going to get quite different lighting on me because of my position relative to the, to the projector. You'd like to get features which are sort of invariant to that, or you'd have to model them. Viewpoint, you'd like to get features, if you could, which are invariant to my different poses. And then also, if you had several different people up here, myself, Jan, or Rob Fergus, or some other speaker, you'd like to get features which are going to be common to all of us, and that may not require modeling the particular texture of my skin versus Jeff Hinton's. So the idea would be, for this, is that you want to try and model certain structures which are insensitive as much as possible, and then from that you could later on build to modeling full general appearance. So in terms of the metaphor for inverse computer graphics, which Jeff Hinton described yesterday, we don't really need to do that directly to get a point. If I take a picture of a car and I want to solve for where the orientation of the car is using a generative model, in practice I could solve that problem more or less just by taking an edge detector, finding the edge maps of the car, and using that to work out where the car is in 3D. It's a classic computer vision thing. It works reasonably well, and it's an approximation to doing the whole thing with a generative model, but it shows you how little you may need the appearance to do various tasks. And also, if you model the appearance in these rather simple ways, that can allow you to bootstrap up to modeling the appearance in more precise methods. So as I say, this work is sort of part of a sort of ongoing research program, so hopefully we'll get to intensity later on. So how do we learn an unsupervised model? How do we do structure induction? Well, the basic idea is really quite simple. You start with a model of the object or the image or the data, which is the default model. And so that's a really, stupid model. It's obviously it's going to be a really terrible model, but it's one that assumes that features of the object are sort of independently distributed spatially. And I'll show a little bit of that later on. Then what you need to do is you need to have a set of rules for changing the model, making it, adding different components to it, etc., building it up. And then once you've got these alternative models, you want to test them by doing model selection to see how well they explain the data compared to, say, the default model or the other models you've got. If they explain the data better, then you've learned something. Okay. So there are various strategies here. A greedy strategy is you just have one model at any time. You try growing it by adding on extra bits to it. If those extra bits modify the data, if the extra bits describe the data better, then you keep that model. And then you search for another model. So you only got one model at each time, and you're just sort of trying to find modifications of it that make it better. That would be a greedy approach. A breadth-first approach is where you have several models at the same time, which may sort of compete, in a sense, to explain data. And then when you combine them, you're sort of going to take certain models together, you're going to see if they're overlapping and so on, and build out from them. So you're not going to commit yourself to one particular model, you're going to commit yourself to a family of models, and then work on that. Otherwise, you can get, otherwise you start having problems, as we found out. So I'm going to talk about three things that I'm probably going to concentrate mainly on the part two, because that's the, I think that gives most of the insight. The first one is sort of what we did historically, and that's really sort of quite simple. And then the next one here, which is a more exciting thing in a sense, is like an extension of this, even though it was actually done earlier. Okay. And so for all these models, I've got different features. And so the first one is going to be learning a model by greedy search, where the features are interest points and then masks. So here we did this, I think that's the data of the journal paper, but the conference paper was a few years earlier. So here you have images from the Caltech data set, and then what you would do is you'd run an interest operator. So you'd find parts of the image which had sort of high cornerness or something like that. And so that meant that essentially you threw away everything in the image that was not interesting. And you can make a lot of progress that way. A lot of the sky area is completely uninteresting. You don't really want to model it. If you have faces, for example, you'd have interest points at places like the eyes, maybe the mouths and so on like that. You'll have interest points coming up at usually sort of significant parts of the object. So, but here you would be modeling the interest points only and the spatial relations between them. So here are some of the Caltech images and some of the positions where the interest points were found on some of the objects. Okay. And so the output would be, from a set of data, it would be a number of different models, which could be mixture components. So for example, in this situation here, the model was fed in some images of planes, some images of faces, some images of bicycles, but the model was not told that there were, which ones were bikes, which ones were faces, which ones were airplanes. It wasn't even told that there were going to be 3 classes of models. It was just taking that data in and then trying to, and then following the procedure that I'll describe. Okay. So here is what you would do. You initialize a default model, and so you take the interest points in the image. The interest points would have certain descriptions about them of their appearance, and so I'm not going to say much about that. You could have a model for the appearance of the interest point. That's okay. But I think what's more interesting is a spatial structure that you'll be getting out. So the default model here is just assume that the images are generated by somebody just taking a set of interest points and just randomly throwing them onto the image. So that's the default model. As I said, it's a very dumb model. It assumes there's almost no structure there at all. But that is the model that you'd start out with, and then you want to do better. So then you can, once you've got a model, which could either be just starting off with a straightforward background model like that, you can grow the model by now looking for triplets of interest points that have certain reliable spatial regulations. So they could be modeled by a Gaussian distribution of their relative positions or their relative positions, sizes, and so on. And so then you can grow the model by adding a triplet of interest points with the probability distribution for their spatial relations, or alternatively, you could add a whole new mixture component, which again would start out with triples. There's nothing really special about triples. It was what we used in the implementation. Triples are nice because you can get spatial properties which are independent of position, independent of size, independent of orientation. So when you do this learning, you don't have to know the size, you don't have to know the orientation. Hinton talked about affine transformations, which is interesting because I think we could have got these to work with affine transformations too, but we didn't actually try to do it. Okay, so model selection. Once you grow a model, so you have a model at one time, you consider several possible ways of growing it. For each way you check to see whether it describes the data better than the model you started out with, and if it does, it becomes your next model. So modeling the data, which would be equivalent, if you think of minimal length description like Rizanen, is you're trying to find a model that gives a better description of the data. So here is a sort of a graphical representation of this. And so this would be your first model, which is assuming that all points are background, and so their spatial positions are just random, and they're generated by that sort of random process. The next model is to assume that the data is generated by a triplet of interest points with a certain spatial relations between them. And so an image would consist of 1, 2, possibly 3 of those types of things, and the rest of the data, the rest of the appearance points would just be background, would be generated from the background thing as before. Okay, so then you could grow the model, and you could grow the model by taking a triplet and adding on another triplet to it to make a bigger model. So here that's just purely background. Here there's a triplet like this, certain structural relations here, and then everything else is just random background. Then as we go from here to here, we've got this triplet, we've added on another component, so now we've got a model that contains 4 interest points. And if we continue in this line, we'll grow on, we'll add another triplet, and so now we have a model with 5 interest points in it. So that's growing a single model, but you've also got the option of growing a new model to say, okay, the data could have been generated by this, but then some of the images are not generated by this model, so now I will try and generate a an alternative model which describes those images. So this would correspond, this thing here, I think, this would correspond to an OR node, so the image would be either generated by this model or by that model. And so if we go back earlier to the, to this sort of data here, the model would start learning, and I don't know quite which object it would pick on first. It would try and find a triplet that maybe corresponded to part of the plane, and then it might grow up that to be, a quadruplet or 5 points, etc. And then it would find there were certain images which that just was not a good description of, and so then it would start, in those images, it would start looking for triples, new triples, and it would start finding these, and then over there it would start finding the bicycles. Okay. So learning, we're learning both the graph structure and the parameters of the model, the parameters being the relative positions of the parts, say a Gaussian distribution over the relative positions of three points. We're also learning the appearance probabilities, but I've left that out of it for simplicity, because that's far more standard. During the learning, we do require a certain form of inference. So, for example, once we've got a model, even a partial model, when we're given an image, we want to know whether that model fits the image well or not. And so that becomes a matching problem between the graphical model and the image, or really more accurately, between the graphical model and the appearance points that you found in the image. And for these types of models, you can use dynamic programming, message passing, or any other model, any other inference algorithm to do that. So when you're doing the learning, you have to have within it an algorithm which can map the model onto the image. Okay, so you have to do one thing to find the best place of the image. The other thing is you have to do model selection. You have to be able to compute for the image how probable is it that that image was generated by that model, and that requires an inference algorithm which is also pretty similar. Essentially, you have to fit the model to the image. If it fits well, then it gives a good description. If there's a model that fits better, then that model is an improved one. So search over the model structure in this way. It's greedy in the sense that we keep one model at each time and then just grow that model. Here, initially, all the data is assumed to be generated by a background thing without any spatial relationships. Expand the structure by using and/or graph grammars, which is just these sets of rules. Once I've got here, I've got the option for adding another triplet on here, or I've got the option for creating a new model here. And those are just a set of rules that we allowed. You could do that for other classes of rules. The thing is, you can't, as you grow it, you've got to, you can't allow it to have too many possibilities to grow because you start running out of computation time in order to do this. The space of our models is really, is immense. There's a sort of an exponential or maybe super exponential number of them. And so you have to have the idea that you can grow the models by finding bits of them and just adding them on. And this is partly the sort of the compositional assumption, the idea that you can learn part of it and then from that you can learn more. You don't have to learn the full thing in one go because that may be just simply too hard. Okay. So model selection, just as a math of this, evaluating the probability that the current model you have models the data, the current model allowing it to be, allowing for the different mixture components to come in, and then you should evaluate this form. You do certain approximations to this to make it simple by sort of replacing this by the max response rather than just the summation over it. Okay. So those methods were quite successful in unsupervised things. You could run them on the Caltech. It wasn't so easy to compare them to other methods because we were sort of, we were giving our methods less than other people were doing. And also to make our methods, to illustrate our methods, we could take the Caltech images, we could scale them, we could translate them and see so that our method would still work. And reviewers wouldn't give us any extra credit for being able to do that. The models, however, here, they're limited. We said we wanted to go with the interest points, because if you have to throw away a lot of an image and only keep little bits of it that matter, the interest points would be the first thing that It might be the first things you'd want to have, but only give a limited representation of the object. So you could take a object remodeled and the positions of the interest points, you could take that out and just have the rest of the object without the bits that you're modeled, and you'd obviously recognize that it was a bicycle or a car or so on, with obviously missing out things. But nevertheless, here the strategy is to try and target the things which are very easy to get at, the things that are insensitive as possible, because then one could build on with the more complex structures later. So for example, we did do an extra piece of work here, which we then extended this to include spatial masks and richer appearance cues. So if the model is generated by, if the image of the object corresponds to a mixture, and the object's going to appear in different orientations and so on, and you can find that out from the interest points, then once you've done that, you could then try and learn a masked model for those different components. If you try to learn the masked model directly without having that sort of intermediate level representation or hypotheses, you'd be faced with an enormous space in which to search. Okay, so now I'm getting on to a second piece of work which was done by my student Rusbek Matagi. And so this was more recent, and this is going to illustrate doing the search in sort of in breadth first rather than in parallel. The trouble with the greedy search was, in some cases, you would get, you get stuck too greedily. You'd find a part, a subpart, a triple that really seems to be quite good, but which you cannot grow, further on to make anything better. So you want to be able to get things which are, can grow more, can search the structure more robustly. So the HOG features, the HOG-Bundles, I think people have talked about HOGs at the meeting, have they? But possibly only as a bad thing to do. So I'll say a little bit about HOGs and then move on from that. They'll give richer descriptions. So here, the compositional approach to learning object models, and so the graphic at the beginning for my student was that you started out with the car, and now this is to sort of try and learn it from these individual bits, to learn the individual bits first. And so here, this would be rotation, scale invariant learning, unspecified number of parts. You don't know how many parts there are. You don't know how many viewpoints. You don't know how many mixtures there would be for this. So going through the talk, there's the sort of the part representation, which is going to be the HOGs, the HOG-Bundles. Then there's the model, then how you do inference on it, and then there's an extra bit about how you add on extra appearance to it. So for the part representation, so the HOGs are a method by which you look at an image, you look at a particular patch of an image, say an 8x8 patch, you compute things like the gradients, and you do a histogram of them. And HOGs are somewhat like SIF features. They're methods that people use a lot in computer vision. They're very popular because they do very nice things. They're also very unpopular among certain people because they lead to solutions which are considered somewhat black boxy and not very easy to interpret. So the HOG representation you'd have for something like these people bicycling is here. If you look into it carefully, you may see edges roughly at the position of the boundaries of the bicycles, the positions of the people. So they do give you that sort of information here. I could give you other images for which the HOGs give you very different and highly unintuitive descriptors. Why they're nice is this idea of sort of insensitivity or invariance. They capture some structure that could be insensitive to the particular type of bicycle, or the particular type of background, and other types of properties, or even exactly the particular place where the bicycle is. So in the sense of trying to model not all the image, but the bits which are insensitive, they make sense to try and use the HOGs and things like that first. They're not ideal, so one of the people who is somewhat skeptical of HOGs is a friend of mine called Ben Kimio at Brown, and so he came up with a photograph of Obama and a photograph of President Bush, and showed that they had exactly the same Hog representation if you manipulated the image. So again, that's sort of a proof that the Hogs do not represent everything. To be fair, that's if you do the Hogs at one scale only, and if you do the Hogs at multiple scales, that will stop it happening. But still, there's a question, a limitation of what the Hogs would do. So the Hogs, this is perhaps more details than you want to know about them, but they look at the image locally. You find histograms, you can represent the histograms, and you get these local descriptions. So the standard Hogs was that you just have a sort of a local 8x8 region here, and you compute the Hogs over it, and maybe you'd normalize by the Hogs nearby. The idea of a Hog bundle, which my student developed, was that you could take the Hog description here and look at the Hog description of the neighboring bundle, and if they were similar, you could sort of group them together. You know, this is like a standard thing you do in computer vision. If you find an edge here and an edge here, you may just group them into a longer edge. It makes sense. As far as we know, no one had actually tried doing that on Hogs to make Hog bundles. The advantage of the Hog bundle thing was, though, if you took an image, and this is an image of a horse in the grass, and you computed first the Hogs and then the Hog bundles, you found that a lot of areas down here in the grass, they would sort of correspond to just sort of one rather big Hog bundle, because basically they're very similar. You know, they've got certain intensity, texture properties of grass, and they're all the same, so their Hog bundle representations would be very similar. Also, if you looked at the head of the horse, or the neck, or the back, you'd find again the Hog bundles were fairly similar along it, because at the back there would be a strong edge between the horse and the sky. The edge, it would be a strong horizontal edge like that, so a Hog bundle in one part of it would be similar to a Hog bundle in another part of it. So if you run the Hog bundles on the images, you got a rather sort of, a pre-processed version of the image, which captured not all, but some of the interesting features of it. And compared to other things that we did before with the hierarchical models based on edges, the wonderful thing about this is that there were not that many Hog bundles in the image. With edges, and I'll talk a bit about that at the end, a problem is that there's so many edges in the image, and when you want to know which edges should be grouped together, you've got a very big search problem. But here, there was only a limited number of them. So you could find Hog bundles from the images, and these would be the basic elements that you'd have. So that would be, in the earlier model, we would just have interest points. You'd have an appearance at the interest point. Here, we'd have the Hog bundle. And then for the description of the Hog bundle, it was really very, very simple, too simple, really. All you did was represent the orientation of the Hog bundle, because the Hog bundle, since it's based on edges, it gives you an idea of the dominant orientation, and then the width and the scale. And you wouldn't model anything else about the appearance. Again, that's really too simple, but as I say, this sort of worked reasonably just by doing that. So your images now would be taken, would be processed by computing Hogs, getting Hog bundles, and then you would group them into, Hogs, group them into Hog bundles. And these were few Hog bundles, special ones, because they were ones that the model learned, and they correspond to the horse, obviously, and these ones do not. Okay, so this is just to show that some of the Hog bundles do sort of correspond to something nice in the image. So a Hog bundle, in fact, that whole thing, license plate, would come out as a Hog bundle. Bicycle frame would come out, horse tail, cat's whiskers, motorcycle wheel, sky, etc. I mean, these are obviously particularly nice examples. If you know anything about computer vision publishing or so on, you shouldn't really trust all the examples that people put in their papers, because they're usually the ones that are cherry-picked to look nice, or at least to illustrate the points. But anyway, so these are sort of rather nicer versions than we normally get, but they're not too unrealistic. Okay. So then the part-based model of an object would be built as a graphical model, and this differs from the models I talked about yesterday, which would be hierarchical sort of compositions. These ones here are more sort of sideways. They're more like standard models that people have done I think dating back from, I think, about 1973, Fischler and Erschlager, Rob Fergus actually had that model put up on his slide. Pictorial structures are examples of this type of model too. And so here this would be, the object would be described by a set of nodes, and the number of nodes is uncertain. You know, this is something that the model would have to learn, and this would be also one component. It would be a mixture of a model like this, another model somewhat like that, and so on. That again would be learned. But the state variables here, the W's, would represent the position, the orientation, the size, and the width and the breadth of the HOG-Bundles. So remember, we're throwing everything out from the HOG-Bundles except their width and their breadth. It's built like this. It's sort of like a type of star model, except this sort of a binary star model. We've got 2 points here and then things coming out from that. That's because if we do it this way, we can sort of deal with the scale invariance rather nicely in a very simplified way. So 2 points are really special because they set the basic size, orientation, and then these other things are added onto it. And so you can have a generative model of the, where you have here a prior model for this. The prior model would depend on the parameters of the model and on the number of nodes. You don't know originally the number of nodes. You do not know the priors of the, you don't know these actual parameters. Those are the things that you're going to have to learn. And as well, the fact you don't know the number of mixture components. And so here was just a little bit more detail about this. This was a distribution of one node versus the other two. These are the sort of the things to deal with the scale invariance and so on like that. But essentially, it's a basic thing. This model is linked to these two, and so if you know these, if you have a model for those, you can learn these conditioned on that. And the scale, their orientation invariant. Then that would be the model of the object itself. Then we need to have a generative model of the image. And so we have taken the image, we've done our HOG features, we've linked them up into HOG-Bundles. And so the image is now represented by these sets of HOG-Bundles, and we have a simple generative model for it. That if we have a HOG-Bundle in the model of the same position, same size, etc., then that would, then it generates a HOG-Bundle of the same type in the image. And we can have a model generated by the object, and we can have the background model, which is uniform, which is our default model, which is assuming that all the HOG-Bundles are just generated randomly and just put anywhere in the image. Or we could have them being generated by a structure model like that, and we then, our strategy then is to try and start off with this, build models of that type, and if they describe the data better, keep them. So it has to estimate things like the number of parts, the number of models, the correspondence between the features and the model. So if we have the model and then you have the data point, you have the HOG-Bundles that you found in the image, you still have to do the correspondence between the model, parts of the model, and the HOG-Bundles in the image, and you have to find the parameters of the image. So a lot of work, I think, that have done things like this before have assumed that most of these things are known. And so here is the sort of the parallel or the breadth first search idea. So initially, everything is generated by the background model, and you can now compute the probability of the data given the background model, the probability of encoding the data in that model, and then you start searching for models where you just have 2 points, a W1 and a W2 with certain parameters. And you can consider several possibilities because you've got no idea what these parameters would be, no idea what these parameters would be, or so on. Some people ask whether we're doing EM here. We're not. We don't want to do EM because EM is trying to fit a single model to the data. We're not trying to do that. This model is considered good if it fits part of the data better than if that part of the data was fit by that background model. We don't want it to fit all the data at all. That would be too greedy to do. We would like to find one model that fits part of the horse, another model that finds another bit of the horse, another model that finds another part of the horse as well. Or one model that finds the car from one viewpoint, another model that finds part of the car from the second viewpoint. Okay, so we will learn several models of these types by estimating parameters in such a way that this model, in conjunction with the background model, will encode the data better than the background. So again, you think of it as being an image. With this model, you think of generating an image by taking several examples of this model and then completing everything with a background. And you compare that, again, as encoding it by just using the background. These ones that survive, that are better, you keep them around, and then you try and grow them. And you try and grow them here by adding a third point on, and again, evaluating whether this model, plus explaining everything else with the background model, is a better encoder than this model, its parent model. So these models just have to do better than their parents. They don't have to do better than their siblings, and that's sort of considered too greedy. For the first model that I talked about with the interest points, is that if we took here, we looked at all these, we picked the one that was doing best, we got rid of all these, we then allowed this one to grow, we found the best way of growing it here, and then we carried on like that. And so that would work for the interest points, at least on the Caltech data set, which frankly is rather an easy data set, but it was not working for us here. So here you want to have these multiple possibilities, keep these around. You have to do better than your parents. You don't have to do better than people of your, your siblings. So you can do various ways of estimating, of coming up with good hypotheses for things to combine together. You could do clustering. If you find certain HOG-Bundles which sort of have a very high frequency of appearing with one sort of 10 inches to the right, then that's obviously a good candidate for a model. A thing here, another HOG-Bundle there of roughly, whose size is roughly consistent with this one, and a certain distance, 10 pixels, 11 pixels, 12 pixels, etc. So if you do clustering, you can find certain compositions or pairs of things that happen frequently in the data, and then you can decide, then you can build a model using those compositions and then try to see if that explains the data better than the previous parent model. Okay, so you can do it by clustering, you can do it by other methods as well. And so again, you have to say this isn't EM. EM would try and fit the data best with one model, and the way of thinking about it is if you think of the EM as having a criterion, like a free energy criterion, it's not that you want to find the lowest one here, you want to find all these possible things. You want to find all the peaks, all the troughs, all the good fits, because those are things that would explain part of the space of the model. The EM thing, though, is too greedy. It's trying to find the best model. We deliberately do not want to have the best model here. Instead, we want to have, several good models that we can then combine together. So you can contrast this a little with, say, one of the sort of a classic deep belief network where you train the parameters from the first model layer to the second, from the first input layer to the first layer, and then you train the ones from this first layer to the second layer. In that sense, you're sort of trying to do an optimality overfitting the first layer model to the image. And here I'd be arguing that that's not always a good thing to do. How do I know what units in my first layer are good until I've given them the chance to combine with other structures in the image? So here, some of the models we learn individually, may not be very good in themselves. This model may be far better than this one, but this one might really be useful. If I take an image of a cat, the boundary of a cat, most of the boundary of the cat is very smooth, and then you have the ears which just stick up. They're really small. If I was just trying to encode the cat's ear, if I was just trying to encode the silhouette of the cat, I mightn't care about encoding the cat's ears because they're tiny. On the other hand, if I want to detect a cat from an image, its ears are the thing which really make it stand out from the background. Look at the silhouette of a cat without the ears, you may not have any idea what it is. Just put in a few little ears here, and suddenly it's clear what it is. So I don't want to be too greedy too early about how I describe the image, because some things could only be could seem very unimportant. This could be, very low in chance of encoding the data because it just says there were 2 ears in it, but then later on, that's very useful. Okay, so here are some of the models that we learn for each category. sort of an apple or Apple logo, bicycle, sorry, not bicycle, bottle, giraffe, cup, things like that. You know, these things, you can see the parts we learn here are not really necessarily semantically meaningful, which is a limitation of these types of models. You know, bits of them do, you know, this clearly seems to be the neck. This looks like the head. These look like the legs. For some of the other models, we're able to get them to be more semantically meaningful. But here, at least, we're getting things which are sort of roughly correct, but not, you know, not quite sort of meaningful enough. Okay, the swan, you have the back, you have the bottom here, you have the neck, you have this, but that's just wrong. Okay, so here is labeling for viewpoint. Here you put it in with several cars or 7 different orientations. It learns a mixture model where this is a model for the car from behind, and this is a model from the car from the side, and it does it without knowing there were two types of cars. Well, I mean, in fact, I think in that data set there were 6 or 7 types of cars. Well, in fact, I hadn't even classified how many cars there are, but that was, you know, roughly 6 or 7 viewpoints. The inference, I mean, it's just that the inference is reasonably straightforward, or at least I'll just refer, you know, sort of standard graphical models. Once I've got a graphical model, finding where it matches the image is just a question of finding the most probable states. That is something that is standard. Dynamic programming, you know, belief propagation, Monte Carlo sampling, anything will do it for you. Evaluating how well it does, again, that's just a computation, that's an inference problem. Standard things work. Performing model selection, just evaluating the goodness of fit of the model, and then going on. That's good. So here's a little bit more details, but maybe I should move on from that because, as I say, this part is basic standard inference. The novelty here is the idea of the set of model spaces and the way that you search through them. Well, in fact, it sort of works. Okay, so then there's an extra stage which is just going to put on certain additional image structures. And so here I'll probably skip over this a little as well to keep up with the sort of 1 o'clock deadline. But just think here, what we've done is we've tried to learn the model using very invariant, or at least insensitive things. You know, I'd love to say that the HOG things are invariant, but a colleague of mine here says I can't use that because invariant ought to be restricted to something that is mathematically invariant. And this is really insensitive, and he's quite correct. So we learn the models of the parts using things which are pretty insensitive. But once we've got the model, once we've learnt the structure of the model, the parts and where they are relative to each other, then you can boost up the learning by putting in richer appearance terms. Because learning the appearance, if you know the structure of the model and you can align it roughly to the object, then there's all sorts of methods you can do for learning appearance, which I will actually won't talk about now, but I'll mention in my talk after lunch. So appearance-based models, so you can put in extra things like histograms, so maybe I'll skip over that. And so you can do these results on various different types of data sets. ETH data set, in-rear horse data sets, car data set, where the car came up with various different viewpoints. And and the method, as I say, gives you a number of different mixture models, etc. It gives you everything in a pretty unsupervised way. I think we were not top score on any one of these, but we were doing pretty close to the top score on this range, and at the time no one else was doing something exactly on that. However, this is a data set thing, and just to say, I don't know, just to give a slight bit of propaganda or negative propaganda for data sets, is that data sets are really, in my opinion, are really good for testing models, but there's a lot of research, particularly in computer vision, which decides that if your method gets 2% better than somebody else on a data set, then it ought to be published. And I think that's a really terrible way to do science, because anyone who works in these things knows that you can often tune things up by paying a lot of attention to details. You can put in so many graduate student hours tuning things up, and you'll do better. And are you really contributing at all? I think, I think here the data sets ought to be servants of the models. We ought to be using the models, we ought to be using to develop novel models and then showing that and then if these models are good, then people in industry who really care about it can tune them up and get high rate performance on it. But spending a lot of time and resources tuning up performance on some data sets is frankly, to me, a complete waste of time. But we can do that ourselves, and so I used to say this, and I was accused of sour grapes, and then we did get good results in the Pascal data set, which is considered strong, which I'll talk about next time, and then people take me a bit more seriously when I make those comments. But most of the senior people will tell you this. Jeff Hinton, I don't know if he said it, but people like that, Jan would agree. So here are the data sets. So here we get nice results in the data sets. Yeah, they're about the state of the art. The method is interesting. It's probably extendable. And this is, is what we can do. To do better on here, we'd like to have richer features, etc. But if we can start getting the structures out using these sort of semi-invariant things, then we can build on that and develop models which are richer and indeed more accurate. So for this part of the work, I think one of the issues would be to put a plug for the HOG-Bundle idea by my student, which is a good idea, and as you can see, gets you quite nice features. Then here, learning numbers of parts models automatically, etc., and the reasonable success on those data sets. Okay, so now I wanted left myself a little bit of time to talk about the compositional work, which is the things I talked about last time. But the idea here is that it's really, so I'll go through the intuitions of it, but the idea here is it's really very similar to the method of searching that I showed there with the HOG-Bundles. You have a background model for generating the data, and the background model for the edges would be what I was calling yesterday a level 1 model, a level 0 model, which would say that the images are made up of edges, horizontal, vertical, 45 degrees, 45 degrees, 135 degrees or something, and they're just generated randomly. That would be a level 1 model. Then for the level 0 model, a level 2 model would be that you take certain compositions of the edges that happen frequently together, and then you would think of generating the image by using a composition of those edges, like a T or like an L. You generate the image by generating a few L's, and then everything else would be generated by the background model. And if that was a better way of encoding it than just the background model, you keep it. So you'd have here a whole sets of different ways of generating the image, which would be generating little bits of it and then filling in with the background models. And you wouldn't be trying to compete with these ones at all. They'd only have to do better than their parent. Because at this stage, you wouldn't know whether this is a good model or this is a good model. There's no way you could do that. Then you could take models together. So if you have a level 2 model, level 1 model that's made up of 3 edges, and another good level 3 model made up of 3 edges, you could combine them together to make a model to say that that composition happens together more frequently, and you could build up here. And you can just keep going. The difference with this method was that here you would take 2 and then you'd add on 1 extra and then you'd add on 1 extra. For the hierarchical edges, you'd take 3 here, you take 3 here, you combine those together to get 3 plus 3 plus 3, which is 9, and then you carry on like that. And so there were 2 papers that we did on this. The first one the input was these images of horses, and where we just ran an edge detector to get the edges. Now on these images, it actually looks easy because the horses are in roughly the same position. That's true. We were not using that information. The algorithm wasn't using that at all. The algorithm was just using this sort of edge map as the input. This would be the description that the level 1 model would give, vertical edge, parallel edge, horizontal edge here, vertical edge, edge at 45 degrees here, vertical edge here. That would be the description of the level 1 model. Then what you would do is you'd start looking for compositions that happen frequently, and so you would find, or the algorithm would find things like this. It would discover longer lines, not surprisingly, because in that image, edges came together. It would start finding parallel lines, because again, in that image, edges were parallel. And so these would be compositions of 3 of these things that happen together more frequently by chance and who gave rise to a model of encoding the data better than just encoding it like this. Then you would grow these by taking compositions of these, this one plus this one plus this one, if they happened, again, frequently in the image with regular spatial structures, and you would sort of discover T-junctions and things like that from the data. So these are nice. These are things that Gestalt psychologists would sort of get out from, would say humans are sensitive to. These are also things to be, that you can get out from other sort of deep belief network type things. Here we're doing it in a different way, building it just on the spatial structure. As you get up to here, everything here looks sort of generic. It doesn't look anything particularly horse-like. As you get up to here, you find that these things start looking like bits of horses. So this is the back, this is the legs, and so on. And once you get up to here, there's sort of no doubt that you found the horse. And with the algorithm, it just sort of stops when it cannot find anything bigger. And so there are 5 layers here, but there's, it's given the option of going to 6 layers, but there's nothing bigger in the image that happens regularly, so it stops automatically. It stops when it finds the bigger thing, and since the images have horses in them, the biggest thing in the image is a horse, and so it stops once it's got that. If the horses came with people on top of it, it would get the horses with the people. I mean, I assume we haven't done that, but there. So here is an illustration of that. Here, where these would be examples of level, this is at any level, but so this would be a description in terms of, say, level L models. The red level L model has found this, the blue level L model has found these things, the purple one's found that, etc. So you would pass the image, you now find these examples in here, and then you'd find that this particular, then you'd look for triples, you'd look for frequently occurring parts, and you'd find that, you find the parts that happen frequently, you'd find this thing only happens once, so okay, it's not frequent, it wouldn't help you encode the image better, so you drop it. You find this one happens several times, you find this one happens several times, these ones are candidates. Then you see, in fact, these sort of interact a bit too much, they're a bit too similar to each other, so you drop out one of them. But this is sort of the basic idea. You build up by finding, by starting with the compositions that you've already got at one level, and then you make compositions at a new level by finding things that occur frequently together with spatial relations. So this doesn't give you a complete horse, because it would be a bit unlikely to, because you'd have to have a third of the, you're building up by threes, a third of the horse way down, but in fact it gives you a set of dictionaries, so once you've got this, the largest element is a lot of the horse, and then you can sort of take other dictionary elements, you can merge them together, you can explore other structures, and you can get a model for the horse out from that. The thing of model selection is that, of structure selection, is that there's so many possible structures. Once we've learnt the dictionaries here, then anything that could be built out of those dictionaries is a possible model structure. And that may still be a large set of objects, but still it's a set that we can explore. So here, if we don't get the horse structure first time, as we do not here, it's legitimate for us to follow a similar procedure, just sort of adding on extra parts from the parts that we've got, seeing whether this, with the extra parts added on, encodes the image better, and if it does, keep it. So that model, that was working on natural images to do edges. It worked on the Weisman data set. It was getting about the state of the art, but that data set is about to be, is I think retired now, because the state of the art is about 95 or something. And so it's no longer a really challenging task. The limitation of that, well, that work also, and I mentioned it earlier when I was talking about the HOG-Bundles, is it builds on the edges. The edges are tiny, there are so many of them, and you're really giving yourself a very hard problem to see whether you should combine them together. Okay, and then the last part, which I'll go over a bit more quickly, is even more quickly, is the issue of learning the edge models for multiple objects. So that was to do with the full compositions, the idea that you can have 120 objects and you'd like to learn dictionaries of parts which you could share between all of them. And here was to remind you, here was the sort of the compositional idea. This is object A made out of part A, part B. Object B is made out of part B, the same one, part C. So you can sort of combine this. You only have to learn that part once, and you could use it for both objects. Yeah, or the or the baseball player, but let me skip over that. Here is the input data, and the algorithm is pretty much as I've described. You start out with a default model, equal, images are just generated by horizontal, vertical, 35 degrees, 45 degree edges. That's your level 0 model. Then you look for compositions that happen frequently in terms of triples. That gives you your level 1 dictionary. That's better at encoding than the level 0. Then you build on from that to get your level 2 dictionary. So that's level 1. Here's level 2, or some part of it, level 3, level 4. And this has actually got the objects more or less exactly in it. So it's the same principle. Start with a default model, give ways to grow the model by looking for small, little localized structures that happen frequently, that give a better encoding. Do this in parallel. Don't be too greedy. Look for different pieces here, 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 here. You can then work out how to combine them together later on. If you have something in here which happens, say, frequently down here at level 1, it may still not be a useful thing to have up, later on. It may be a part that corresponds to noise. It may not correspond to the object. So you can have quite a large number of possible level 1 dictionaries, and then you can sort of prune them out later by finding that they're never used later on. There's a small part here. It's not used later on. It doesn't help later on, so you sort of drop it out. So that's again to talk about the not being too greedy or too optimal early on. There could be something here which only happens a few times, like the cat's ears, but which is really important when it's combined with other things. And there are other things here which happen frequently, but they're not really useful. They don't build up onto anything. So the algorithm that we did for this was basically the algorithm we'd done on the image, on the data on the horse image, except now we did it on the boundaries of these 120 objects, and the parameters were changed slightly, but essentially it just ran, and it gives us these models. And again, remember, these are sort of probability models. These are the mean configurations of the distribution, but these are sort of all, you should think of these really as being sort of deformable, flexible things that could model. And there's issues about how you share parts. As I said, part sharing is good because it needs less data to learn, because you only have to learn the part once. Also doing inference, if you find the part and the part could correspond to any one of these 120 objects, then you're saving yourself 120 amounts of detection. And so there were certain graphs here which were saying the value of doing this by having these by having the sharing parts. Okay, so I guess I should stop now. So here, this talk was on the unsupervised learning of the graphical models coming in from yesterday. Basic things, start with a default model, build new models locally out of little bits. That's the sort of compositional idea. Don't be too harsh early on. Something that may not look very good, but is better than nothing, may turn out to be a very important component later on. Grow the models by putting them together. And so that's really the sort of the breadth first search idea rather than the greedy one. Okay, so that's the end of this talk, and so I'll finish now, and then my talk after lunch will be actually about more sort of discriminative methods and dealing with things like the Pascal data set and so on. Okay, well, thanks for your attention.